There's no denying that if you're working on anything analog, be it a simple 1-amp circuit or something more complicated, it's really convenient to have a voltage rail that goes below your system ground. Unfortunately, for a hobbyist, it's not that easy to generate a negative rail that is both adjustable and regulated.
Sure, if you have the money, you can just buy 2 lap power supplies and tie the positive of one to the negative of the other, as they are galvanically isolated. You could also build your own symmetrical power supply by taking a transformer with a center tap secondary, rectifying and filtering the output, then using 2 adjustable linear regulators. I had a transformer like that, but with adjustable secondaries, which allowed me to skip the linear regulation on the output. If you only need a minuscule amount of current, you can get away with a switched capacitor converter, like the 7660, or, more likely, a diode capacitor network driven by a microcontroller, which is a nice technique to keep in mind, but there's no regulation there, and the output voltage really does depend on the load current.
So there are solutions, but everything I've just mentioned is either very expensive or very involved. Now, I know that that's where part of the fun of being an electronics hobbyist is, building stuff like that. But if you're just trying to work on something else and need a negative voltage rail, it would be nice to have a quick and easy way to get that.
Like, if you want to have a voltage that's lower than the one you have available, you can just grab one of these buck converters for, fittingly, around a buck, shipping included, from China. It uses one of these hyper-integrated switch mode power supply controllers and is an actual inductive converter, so you can easily get 80% efficiency, and it has no problem supplying over an amp of current. It also has an integrated bandgap reference, and the adjustable output voltage really is regulated, so it won't change with load current or temperature almost at all. If you want a voltage higher than the one you have available, that's no problem too. You can get a board like this in a boost configuration that allows you to do just that for pretty much the same price. Buck and Boost are the names of the 2 simplest switch mode power supply topologies, and there is a third one that's just as simple, called the inverting topology. It allows us to get exactly what we are looking for, a negative voltage the absolute value of which is either higher or lower than that of the input. It would be nice if you could just buy another blue board implementing that topology for a buck from almost every online electronics store, but unfortunately you can't. So I started wondering if and how you could mod one of these boards to generate negative voltages, and would it even be feasible. I found this schematic of the buck converter module online, which matched my board. I also found this schematic in one of the datasheets for the LM2596 IC used here.
They're the same picture.
Well, not quite. If you look at the simplified diagrams of the buck and inverting topologies and perform some mental gymnastics, we can sort of see that they are kind of the same. A diode from the switch to the negative output, an inductor from the switch to the positive output, and a filter capacitor across the output. So, it would seem that if we use the usual arrangement of input voltage between in plus and in minus, and output voltage between out plus and out minus, we are using the board as a buck regulator. However, when we attach the input voltage between in plus and out plus, and take the output from between out minus and out plus, using out plus as a ground, the board will work like an inverting converter. And what do you know, it really does. We can get larger or smaller negative voltages.
Just before you click off this video, there are a couple more things you should know, like how it works and when it won't work.
As for the first thing, to quote the datasheet, this circuit converts a positive input voltage to a negative output voltage with a common ground by bootstrapping the regulator ground to the negative output voltage. Think of it like this. You're lifting a box. This is the buck mode of operation, and this is the inverting one. You're performing the same movement. It's all a matter of perspective. Have useful analogies aside, if you can wrap your head around the fact that the LM2596's ground is different than the input ground, and the input voltage it sees is a sum of the actual input voltage and the output voltage, then you'll know what's going on here. So if, for example, you're converting 12 volts to negative 6 volts, the chip sees 18 volts at its input. Here we have our first limitation. The IC is only rated for 40 volts on the input, so we can only go so low with a given input voltage before the chip breaks. Also, the controller is rated for 3 amps, but that is only the switch current. While in a buck configuration it is the same as the output current, this is not the case here. The fraction of the switch current which goes to the output is dependent on the input and output voltages. Let's assume, as before, that we are converting 12 volts to negative 6 volts. The IC sees 18 volts at its input, 12 of them from the actual power supply, and 6 of them from itself. Oh, the joys of bootstrapping. Then 6 18ths, or 1/3, of the switch current rating kind of goes back. Don't yell at me for this explanation, the math works out. And the remaining 2/3, or 2 amps in this case, can go to the load. Just remember, it's only a rule of thumb, and the actual maximum current will be less. So, reduced input voltage, reduced output current, we can live with that. Even when reduced, these ratings are still quite high. Unfortunately, the last thing we have to watch out for is the startup input current. After the converter starts, it consumes very little current. But right at the start it may need as much as 5 amps for 2 milliseconds or longer, and not all power supplies will be able to deliver that. To make matters worse, the current won't go down until the converter starts. So if you're powering this from a constant current limited power supply, it may never start. But we can try to get around that. Anyone who's ever designed a lab power supply knows that if you want active current limiting, you cannot have an excessive output capacitance, as even if the active circuitry shuts the output off, the capacitor still needs to be discharged. We can use that to our advantage here, by adding a big bulk capacitance on the quote-unquote input and delaying the startup. The latter is done by attaching this resistor capacitor network to the on-off pin. So, again, what we're doing is relatively slowly storing some energy from the power supply in the input capacitor, and then switching the converter on and using it all up at the same time. As for calculating the exact bulk capacitance required, don't bother, just go with what you have on hand. I've been down that road, but we're not designing anything from scratch here. We're just trying to make sure a $1 regulator board starts up. I mean, for crying out loud, a real LM2596 from TI costs 20 cents more than this whole board, and that's when buying over 1,000 units, so it's not like we can rely on what it says in the datasheet with this obvious fake. Some experimentation is gonna be required. The RC network values I use should give us a barely noticeable startup delay, at least in this application. Okay, I lied. There are 2 more things to think of. Let's go through them really quickly. Now, we have a giant capacitor between the input and the output, which creates a high-pass filter with the load. So the TI datasheet suggests adding a Schottky in series with the input to prevent noise and ripple coupling under small loads. On a related note, we're now lacking a capacitance between the input and the ground, so we should add like 100 microfarads or something here. So, after lifting the enable pin, which is pin 5, and soldering in the resistor capacitor network meant to delay startup, and soldering in a series Schottky on the input, and adding an input capacitor, and soldering in the new bigger bulk capacitor, we finally have a fully modded board. Yay! It works, even when powered from a current limited power supply. That's great. Sure, if you listen to my explanation, the mod may seem lengthy, but it's actually pretty simple, and some of you may be using a power supply that doesn't care about the big startup current, and therefore don't need to make any mods at all. So yeah, that's why I think this is the simplest and cheapest method for generating negative voltages for the average hobbyist. Obviously, with switch mode converters there is the ripple in the tens or hundreds of kilohertz range to worry about, and you know, this may not be acceptable depending on the application, but if I haven't made it clear before, when I said analog electronics, I wasn't talking about hi-fi audio or anything like that. I mean, there's much more to analog electronics than that, and not everything requires microvolts of power supply ripple. I should probably make some ripple and efficiency measurements now, but this video is already long enough, and I'd probably make some dumb mistakes if I try to do it now.
Anyway, that's it for this video. I mean, I know using a buck converter in this way is not anything groundbreaking, it's in the datasheet for heaven's sake. But I think I'm the first person to put 2 and 2 together and realize that you can use this $1 board in this way.